Yep. So if you look now at the YouTube page of the Master HPC, that's the link I just shared with you in Jitsi. You should be able to see a live stream that it's being recorded, and it's the so you can if you want, you can close Jitsi so that you don't have two different streams doing exactly the same. You can hopefully, I'm going to go there to my own live streaming. Okay, so you can type in the chat. Okay, and I will be able to read you. Okay. Good. So let me move my laptop to use the whiteboard. Let's start the class. I'm going to be using, essentially, I'm going to be using my shared screen. That's why I'm using Jitsi instead of Aula Sesga. But I'm going to start by giving you some notions of what we're going to see today on the whiteboard. Okay. Okay, so you will remember that last week, last week we could work some with Python, and we tried to do some data analytics using just pure Python. And in order to do that, we parsed some HTML page, and we also worked with XML and also with JSON, and you could see the let's say disadvantages of working with just pure Python. You had to do the parsing by yourselves. You had to deal with things like missing data yourselves, and etc. Okay. What we will see today is a library called Pandas that hopefully will be much easier to use for doing data analytics in Python. Okay. So the idea is the following: imagine that you want to have a indexed array. For instance, that could be an array which contains the values of a certain stock. Let's say, for instance, Google stock. Okay. So you could have an array like this. Okay. That will have endpoints of data. Okay. So some value up to some value up to m, from 0 to m minus 1. Okay? In order to know how that corresponds to dates, you will need to add another array with exactly the same shape. Okay? So this will be a data array. And you will have an index array. And the index array will have exactly the same shape as the data array, so n elements. Okay. And elements should be collocated with elements in the data array. So essentially, if you take an element over here, let's say element k, that should be the date for the value in position k of the data array. Okay. That's the thing that we want to model. Okay. So you can use this. You can use these will be two different NumPy arrays, and this is all good, but it has some issues. For instance, imagine that now you have different stock that you also want to track. If this was, imagine, Google stock, this pair of arrays is Google stock. Okay, that's ticker GOOG, and you now want to compare Google stock with, let's say, Apple stock. Okay, if you want to have Apple stock, then you need to use again 2 arrays. One which contains dates, so that's the index, and data array which contains stock values. Okay? So you have something like this. Whoop. Another index array, and another data array. These 2 track the values of Apple stock, that's AA1. And it works in exactly the same way. So position K prime, or let's say position K, okay, in the index array indexes position K in the data array. So it lets us know which date corresponds to the value in the data array. Okay. This might be. I don't know whether it will be a bit blurry, but let's hope that it's at least readable. Okay, I'm not going to use the whiteboard much. So, so now the problem with this is that you have n values for Google, but you might have a different number of values for Apple. Let's say n-1. Because maybe Apple started, for sure, started I forgot the word, but entered, let's say, the stock market before Google did. Okay, so you will have many more values related to Apple than you will have for Google. Okay, so the first thing, imagine that you want to know whether Google has a higher value or a higher stock value than Apple, okay? Then you need to first, let's say, align the index arrays so as to know how K in this index array, let's say this is January the 2nd some year, where January the 2nd of that year is in the index array of Apple. Okay? So the first thing you need to do in order to do operations which involve both arrays will be to align both arrays in the indices. So this is starting to be a bit cumbersome. You have 2 different arrays to index data. If you want to look for a date, for a particular date, then what you can do is to just search in the index for the date, and then once you obtain the position K, which corresponds to that date, you just go to the position K in the data array. That's fine, I guess. But every time you update the arrays, you need to be careful to update the arrays in the same way. Imagine that you add 1 day at the end of each data array. You need to add 1 day at the end of the index array. If you add some value in the middle of the data array, you need to do exactly the same for the index array. So you need to be careful to preserve the referential integrity between both arrays, let's say. And when you start operating with different arrays, imagine that you now want to compute the correlation between these values and the values of Apple, and then of Microsoft, and then of IBM, for instance. You need to align the 4 data arrays and start doing operations very carefully. Okay. Now imagine that there's 1 day which is missing for some reason in one of these data arrays. Imagine that, for instance, Apple did try to acquire some other company, and for that reason, the regulator just decided that for a particular day, Apple stock was not to be traded. Okay. So then maybe you'll have a data point for Apple. You have to keep track of all of those issues in order to be able to operate different data arrays. Okay. You have to deal with missing data, you have to deal with lots of things. Okay? So that's the problem that Pandas comes to solve. Pandas was developed by I think he's a mathematician called Wes McKinney. He based Pandas on R, on the statistics language, and he decided he wanted to do something like that, but in Python. Okay? So he developed pandas, and the basic idea in pandas is to provide this object, something which encapsulates at the same time the index and the data array. And this is called a series object, okay? Panda series. Okay? So instead of having two different array objects and being in charge of managing our indices and everything related to the indices and the data, what you will have is series objects, which internally encapsulate both the index and the data arrays, and they use NumPy arrays. It's not different at all from what you manually do, but the idea is that Pandas library is going to do all the nasty stuff for you, all the nasty stuff which is behind the operating and doing data analytics in that way. Okay? So this is the one-dimensional object. And then we have a two-dimensional object which encodes what's the name? Tables of data. That's called a data frame. But let's see series first, and then we can move to the two-dimensional object later. Okay. So what I'm going to do now is I'm going to share my screen. I'm going to start working with Anaconda, with a Python interactive session, so that you can see how to work with pandas and hopefully with good image quality. Okay. Is everything all right up until now? Could you see the whiteboard or okay? And can you hear me okay? Hopefully. Okay, great. So I'm going to share my screen now. Just 1 second, because maybe I can do something better. So that would be okay. Okay. So here. I hope this is, I had to switch from Firefox to Chrome in order to be able to share my screen. And I hope this is now being recorded. Let me double check. Okay, I think it should be working. So let me now finally share my screen. Okay. Let's see, YouTube is recording this nice. Yeah, wait, that's great. Okay, so let me just do this. Okay. So hopefully you can see the screen well enough. So as I mentioned, this series object will be something that encapsulates at the same time an index and a, let me install one package really quick in order to be able to in order to read data quickly. I'm going to install Pandas data reader package, which is capable of acquiring data really fast from, for instance, the stock market and etc. So I thought this was included off the shelf with Anaconda, but clearly it is not. So the idea when you use Pandas, it's always imported like this. I mean, it's conventional really. So you import Pandas as PD, and then you can, for instance, create a new series like PD series 1, 2, 3, 4, for instance. So you pass it one list, for instance, and you get this series. As you can see, it has two different columns. The column on the left here has the index. By default, I didn't any index object. So by default, it's using correlative integers. And the second column, that's values, as you can see, 1, 2, 3, 4. So if I were to use, for instance, pd.series 4, 9, 12, 15, this is what I would get. 0, 1, 2, 3 is the index. 4, 9, 12, 15 is values. Okay. Let me just finish installing this Pandas data reader object. So hopefully I can import it, Pandas data reader as web. So now I can import some data. For instance, if I want a Google stock, I can do web get data Yahoo, and I pass this array. This is ingrained. So and pass a ticker. So I will get really a table, but I'm going to extract a series, since that's the first thing that we're seeing. And we will talk about the table that I'm actually downloading later. Okay, so here you have the Google stock values for different dates. Get data Yahoo actually returns data from 2010. So the first day that the market was open in 2010 was January the 4th. So that's what you have here. January 4th, 2010, Google was valued at, closed at $311. And you have 2,314 data points up until May 14th, 2019. Okay, that's today, actually. So, yeah, that's all the days that the market was open since 2010. Okay, I need to do something very nasty to see if you're asking any questions, which is to open Jitsi. So yeah, this is going to happen. But that's the only way in which I can read the chat. Okay. Okay. So that's. So as I mentioned, this is actually a series object, but it's built on top of two different objects. One is s.index, and you have here, sorry, that's not s, that's Google _s dot index, okay? And that's an object of class date time index, which is a class which is derived from a NumPy array. And as you can see, it's a special time of Pandas index, which contains dates. Okay? And you have another array, which is values, which is an array with exactly the same shape as the index, which was 2,300 points, and which contains the values for those indices. So this is exactly the same concept that I mentioned to you. It's two arrays of the same shape, and the index array gives you the dates which correspond to the values array. Okay. So now what can you do? What you can do with the first thing that, let's say, Pandas provides is indexing. So you can just ask for a particular date, let's say, for instance, 2014 December the 18th, okay? And it will give you the value at which the Google stock closed. Okay, you can just input dates in string format, as you can see. You could use, this is the UTF format. You could use also the European format if you are so inclined, 18/12/2014, and that will work. And you can even use the American format, 2014. Problem is when you use a ambiguous date, imagine that you say 03/04, okay, that's going to be, I think, American format. So that's 2014, March, 4th of March. Okay, it's not the 3rd of April. Okay, so keep that in mind. In any case, good habit is to just use UTF-8 format for dates, and in that way, there's no confusion whatsoever. Okay. What else? You can, since these are dates, you can ask, for instance, for a full month. Okay, you just type 2014-03, and that's the full month of March 2014. And you could ask, of course, for a full year. And that's all the points that you get in a full year. Okay, you can ask for a range of dates. Imagine that I want from December the 18th up until December the 31st. So that's up until the end of the natural year. So you can just use the slice syntax, and that will work. Notice one very important difference with how NumPy arrays work, and it's that this interval that you're getting is closed. Closed on the left and also closed on the right. If you remember how it worked for NumPy arrays, if you have a NumPy array which contains, for instance, numbers from 0 to 99. Sorry, I have to import NumPy. Remember, if I asked for the interval 40 to 57, you will get from positions 40 to the position 56 included, but not the 57. So it's open on the right. Okay? That, for some reason, is not the case with pandas. It's closed on both ends of the range. Okay, so keep that in mind when you write index ranges. Okay, of course you could just say the step. You could just say skip every second day. Okay. So that will work properly. Just one thing I would recommend. But this is just for consistency. You can do this, but I recommend you use .log. Okay? And I will explain later why you will want to use Google .log. Okay? If you want to index the array using the index array, so that may be a bit less confusing. If you want to index a series using the index, you can use log. If you want to index the series by position, you can use ilog. So, for instance, ilog 10, that is the 10th position in the array. Okay? And you can use ranges in ilog that works exactly the same as a NumPy array, but again, it's closed on the right. If you count, there's 10 values. Sorry, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. No, it's now open on the right. So this works exactly but like NumPy arrays, but indices work differently. It's closed on the right. So that's something a bit confusing at first, but it's just how it works. I recommend you use log and ilog for several reasons. One of them is that you can do this. Okay, you can just index this series, using an integer, and since this series is indexed using dates, it will not be confused as to what you mean, and it will use ilog. Let's say it will use position-based indexing. However, if your series is integer indexed, then that's different. You can do something like this, for instance, 4, 5, 6, 7, and the index is pd.index, and you use different index, which goes something like 9, 10, 11, 12. Okay. It's not np.series, it's pd.series. Okay, so you have this. So if you use s.log, for instance, 11, that works. That's index 11. If you use s.ilog3, that works. That's the position 3 in the array. If you use s3, that gives you a key error, because since it's integer indexed, it's trying to interpret this integer as an index, not as a position. However, it's quote unquote smart enough to know that the Google array was date indexed. So if you use an integer, it will know that the only way in which it can index it is using position-based indexing. But to me, that's just too confusing to let pandas use its magic and do whatever it thinks it's best. So I just use log and ilog to actually remove the confusion and explicitly say what I want to do. Trip time again to see whether you have any questions. I see you don't. Okay, so moving on. Another nice thing that Pandas provides is array-based, let's say, array operations on series. So if you want, for instance, to multiply this array of values, picture it this way. Pandas series can be used as an array. And in that case, the array that Pandas uses is the values array. So for instance, if I write group_s and multiply this by 2, what it gives me is a series with exactly the same index as the original one, but the values have been multiplied by 2. So see, for instance, for the 14th of March, the value was $1,190 for one Google stock. If you multiply it by 2, you get twice that. Okay. And it can work also as a dictionary, because you have kind of a hash table, right? You can just index using whatever you want. So series work as arrays. When a function wants to receive an array, the series will work as dictionaries. When a function wants to receive a dictionary, it will work as a dictionary, and also have functionalities beyond those two, as we have seen. Okay, so they are, I think, pretty nice objects. You can index arrays beyond, series. You can index them beyond just using just one element or using range indexing. You can index them in the same ways that you will index a regular NumPy array. So that includes, for instance, Boolean indexing. Imagine that, so I have, remember my array has 2,314 points. So I can just build, for instance, a Boolean array containing, again, 2,314 points. And I'm going to call that mask. And that's an array, which imagine true, false, multiplied by 2,314 divided by 2. Okay. So, yeah, I need to do this like this. So if you're yeah, this is Python 3. So if you're confused by this syntax, what I'm doing is when you get a list and you multiply it by a number, what that does is concatenating the list and adding each. So creating, for instance, 3 copies of the list and concatenating them together. So I built an array containing, hopefully, 2,314 points, which has true, false, true, false, true, false, just like that. Okay. If I pick my series and I index it passing a Boolean array, it will give me an array where, a series where I have a value for each true in the mask array. So as you can see here, I have 1 out of each 2 days, the 4th of January, 6th of January, the 8th of January, and so on and so forth. Okay, so that will work. This is not very useful, but the thing that is particularly useful is to ask for something which is to use a Boolean mask, which is computed by using the values of the array. So imagine something like this. I want to know when the Google stock closes over $500. Okay, so I can just do this. Book underscore s greater than 500. Since this is it behaves like an array, what it's going to do is it's going to broadcast. You remember that concept we discussed last week. It's going to broadcast the 500. It's going to build an array of the same shape of the number of values in GoogS, and it's going to return true and false element-wise. So this is what I get. Okay. In 2010, Google was under $500. Now it's much higher than $500. Now it's always true. And I'm going to get an array with true and false. It just has one true when the stock value was over 500. So I can just use that array to index GoogS. Okay. So this will be akin to doing kind of a select star from Goog stock where value is greater than 500, okay? And it's going to return the subseries, which contains the data points which have stock values over 500, okay? Which is pretty nice. Yeah, it comes in quite handy, okay? You can use, of course, any Boolean array you want, but particularly the ones that you compute using functions over the values of the series you're indexing are usually the most useful ones. Okay. You can do also fence indexing. You remember fence indexing was when you passed a list of data points that you wanted. So you can, for instance, ask for 2014, 12, 18. You can ask for then 2015, 03, 01. And then you can ask for 2017, say 12, 11, okay? That, oh, sorry, it should be, no, this might not work. Oh, yeah, sorry. What I did wrong was to use different arrays. I should just use one array, 3 data points. Oh, I see the issue here. I think the issue here is that I can use google.f.log 2014, 12, 18, and that will work. But if I want to do fence indexing, I need to use the date time object. So hopefully I can do that. Like this. I need to use date objects. Let me try to do that. Let's see if that works. So that will be date 2014, 12, 18. Okay. So now I might be able to use fence indexing by passing different dates inside an array. 03, sorry, 3, 1, and also date 2017, 12, 11. Okay. So it's just that it's not capable of doing fence indexing with strings and converting them to dates. So if you had, for instance, an array series which was indexed using integers, then you can do fence indexing just regularly. But if you are using dates, you need to use date objects for fence indexing. Okay. See, for instance, that there was no market on March the 1st, 2015. That's probably because it was kind of a off day. So I can go to 2015, March the 1st was a Sunday. So it's returning not a number. So it's returning a missing value as we would expect. Okay. One very nice thing that you can do with a series is to just use any NumPy universal function. You remember that we discussed NumPy universal functions last day, and this was a function which was applied on an array and which was applied element-wise to all the elements of the array, but this was very fast because it used C. Okay, so you can apply any of them. For instance, you can apply exponentiation to your good.s array, and you get, yeah, that was probably not something nice to use, but np.log, and it will apply a logarithm element-wise to each element, yeah, of course, element-wise to your series. Okay. One very nice thing that Pandas is going to provide is index alignment, of course, automatic index alignment. Okay, so imagine, for instance, that I were to obtain two misaligned series. So I'm struggling to think of a technological company which didn't which was in the market. So let me use car companies. For instance, I'm going to use Tesla, since I know it started being in the market after January 1st, 2010. So I'm going to get the data from Tesla. Let's get data Yahoo TSLA. I'm going to get the series, which contains only the closing values, and I'm going to get the data for Ford. Let's get data Yahoo F. Okay. And then series with closing values will be Ford.close. Don't bother. Don't worry about the dot close. That we will explain that in a few minutes. Okay. So now I have two series. If you look at the series Tesla, this head function tells the series to show me just the first 5 data points. Okay. Tesla, as you can see, entered the stock market on June the 29th, 2010. Well, Ford has been there probably forever. Entered, so it has data from January the 4th, 2010. If I want to know whether Tesla or Ford is higher, then what I can do is just Ford S greater than Tesla S. And this will return, sorry. Whoa. Yeah, that's a strange thing. It doesn't let me just use greater than, but it does let me use Ford minus Tesla greater than 0, which is exactly the same, right? So I'm going to use that. So as you can see, I can just do that, and I will get, yeah, I know why it's failing. So when I do Ford and I subtract Tesla, see what happens. The first data rows are not a number because there's no data for Tesla there. So what Pandas is telling me is that it cannot compute Ford minus Tesla for that particular date because there's no data for Tesla. So it just returns none. When I then do Ford minus Tesla greater than 0, what it does is try to compute whether that was greater than 0 or not. And for nonce, it returns false because, yeah, it assumes that none is not greater than 0. Okay, you could think that it could return just none, but that's a problem since this greater than 0 comparison needs to return a Boolean object, and none is a float. So either it returns something which is a mix of Booleans and floats, so not exactly a NumPy array, or yeah, it's a NumPy array, but not a native C NumPy array. Okay. Or yeah, what it can do is next best thing, just consider that 9 is not greater than 0, it's probably not less than 0, and it's not equal to 0 either. So it's 9 is just 9. Okay, when it comes to Boolean comparisons. Okay, so I want to know, I come back to the problem of knowing when Ford stock is higher than Tesla stock. Okay, and as you can see, it performed date alignment or index alignment automatically and very nicely. Okay, it dealt with missing values automatically as well. So that's very cool, I guess. If you want to know how many times that happened, I don't know whether I mentioned this, but if you dot sum an array of bools, you get the number of truths you have in the array, which is 0. So Tesla's stock value was never under the fourth stock value. Okay. So that's as you can see, that's what happens when you operate into different series. It just automatically aligns the series. So you can do nice things like, for instance, Tesla.core with Ford. Sorry, Tesla_s.core Ford_s, and it will give you the correlation between both stocks. Sorry. And quite surprisingly, there's a negative correlation between Tesla and Ford of just minus 0.12. So if we were to compute the correlation with Google, that's much higher. So that's 0.90. So one thing we have learned by just this very simple analysis is that Tesla, even if it builds cars, behaves much more like a technological stock than it does like a car or car manufacturer stock. Okay. So any questions up until this point? Let me stop sharing my screen just so that the infinite recursion stops. I'm going to use the whiteboard again in a minute, but if you have any question, now is the time to cover that. Okay, so if there's no questions, let me just introduce you briefly to what data frames are. Okay, I'm going to try to use the whiteboard, same as before. Over there, it might be a bit blurry, but hopefully it will be readable. Okay, so the concept of a data frame is quite easy to understand once you have understood the series. So with series, you have one index and one data array. They have the same shapes. A data frame is an extension of this idea. You have one index and several data arrays. Okay? And that's a single object. So essentially, imagine that you had, in our stock example, for Google, you do not only have closing value, but you can also have opening value, higher value, lower value in the day, also the traded volume, and percentage of variation between this day and the previous one. Okay, so you have something like this instead of having that. You will have something which is an index, which are dates. Okay. Okay. You have a number of columns, which are different data series recorded over the index. And you have a two-dimensional array here, in which a cross-section of one row represents all the values in the series, in all the series for a particular day. One column represents all the values for a given series for all the dates recorded in the index, and the cross-section is a particular value for a particular day. So for instance, the closing value on December 18th, 2014. Okay. So I hope, yeah, that's a bit blurry, but I hope you can at least make out the figure. Okay, you have, that's essentially different indices. Okay, one which gives you the dates, and the other index somehow indexes your data series. You might have, for instance, the close value, as I mentioned, the opening value, etc., etc. Okay, you can figure, so conceptually, this is exactly the same as an Excel table, for instance, and also exactly the same as an SQL table, at least from the conceptual point of view. These are just tabular data. Okay. And otherwise, it works exactly the same as a series. And in fact, it's built up from series. So I'm going to show you now how that works. I'm going to share my screen again and start working with and in order to avoid having infinite recursions and etc., I'm just going to share the window of the Qt console. Hopefully, yeah, I think that will be enough. Okay, so imagine that I have, for instance, I have, you remember that I obtained, what I told you was that the value I obtained using get data Yahoo GOOG was not a series, was a table, okay? And this is what you have in that object. It's exactly a data frame. You have the date index, the same as we had in our series, we just had the close values, okay? You remember that I did something like goog.s equals goog.close. So what I did was to extract the close column from this data frame that I downloaded, okay? So this is what you have. You have essentially 6 different series over the date index. You have the highest value, the lowest value for each day, the opening value, the closing value, the volume of traded stock, and the H close, which that's adjusted close. So that's essentially what the value will be if you take into account splits, dividend, and etc. Okay. Okay. So let's see what we can do with these types of objects. We can index them exactly the same as we would index a series object. So goog.log, and I give a date. And now instead of returning just a single data point, what I get is a series, which is a column. A row of my data frame. That's 6 values, one indexed with high, one with low, open, close, volume, and adjusted close. Okay. I can index via the column. For instance, I can ask for the column close. Okay. And that's a series which contains all the closing values for all the dates in the index. So this is exactly the same as the series which we were working with before. And look at the difference. If I don't use lock, the brackets operator indexes over the columns. So it gives me a full column of the table. If I use .lock, that indexes over the rows. So it gives me a full row of the table. And that's why another reason why I recommended using .lock when working with series, because in that way you are able to use the same syntax when accessing series and when accessing data frames, and it's a bit less confusing. Okay, just using the brackets in data frames indexes over the columns. Okay, so you need to use .lock to use the index actually. Okay. Other than that, you can do with data frames the same you did with series. Okay, so it's not different in any way. But now you have goog.index, which is the datetime index. You have goog.columns, which is another index object, but which now gives us the columns we have. And we have goog.values, which, as you can see, is a two-dimensional array, shape 2314, which was our number of rows, and 6, which was our number of columns. Okay, so that's a NumPy array. And the nice thing of using NumPy arrays is that any operation on pandas data frames and also on pandas series will retain the very high performance of NumPy. Okay. So you have any questions with the concept of a data frame? Okay, great. So when you access a particular column, you can do it like this, like I did before, using the name of the column, using a string inside brackets, or you can do something which is usually faster, which is just use an attribute named exactly like the column. That is created automatically by Pandas, so you can do just that. Okay. The only case in which you cannot use attributes is when you have a column which uses, for instance, a non-ASCII character, for instance, accents or something like that, or you use maybe at symbol or something that was not included in the original ASCII alphabet, or so it's if you use a dash for something like that, a slash, anything that is not a valid variable name will not work, and then you have to revert back to using the access or using brackets. Okay, but other than that, you can just use dot variable name, and that will work. Okay. There's a very nice thing that you can do with pandas, which is plotting very easily. See, if you, well, it's a kind of small plot, but hopefully a bit larger. Okay, so for me better. So that's so as you can see, I just plotted the close series. That's the closing values for Google, and you can see that automatically you get a very nice plot with in the x-axis you get the dates, so that's the index, and in the y-axis you get the value of the series, so that's actually the closing value. Okay, you can ask it, for instance, to be by default it's going to do a as you can see a lines plot, but you can ask for any kind of plot, for instance, scatter plot. Okay. Oh, that only works for data frames. So I can do goog.plot kind equals scatter. On the x-axis, I actually want the index, but let me use whatever so that you can see how it looks. The highest value on the y-axis, I want to see the lower value, and that should be it. Oh, sorry, and the fixed size is 20 times 15. And you get the scatter plot. Okay, the higher the dispersion on the y-index is the, let's say, more turbulent the day was. Okay. In this, you can use bar plots, you can do box plots, you can do lots of different types of plots. You have all the kinds. If you, if you just do goog.plot and ask for the kinds of plots you see here: line plots, bar plots, horizontal bar plots, histogram plots, box plots, kernel density estimation, area plots, pie plots. There's plenty of different types of plots you can use. Okay. On this particular plot that we did here, which signal the difference between the higher and lower value, we can analyze that using, let's say, not graphics, but analytics. So you can do something like high minus goog.low. And that will give you a series which gives you the spread of the value stock in a particular day. Okay, and you can ask, for instance, what the max spread was. You just use max, and as you can see, I'm using parentheses here because goog.high minus goog.low is a new series, so I use parentheses. So the max is called over the full series, and that's $101, which is, well, quite high, and that happened on the 29th of October 2018. I'm not sure what happened on that day, but we can probably look at the news to see what happened. And if I want to know the percentage of the spread, I can just do goog.high minus goog.low divided by goog.log 2018, or even better, 2018, 1029. Okay. Well, let's see. Sorry, divided by goog.log. Sorry, no, that's not correct. Let me do this. Goog.high minus goog.low, I'm going to call that s.max divided by s.max. Okay, so this will be google.close.log s.indexmax divided by s.max. Yes. So what I'm doing is goog.close, so the closing values in the day where the spread reaches its maximum. Remember that was the 29th of October 2018. So I do goog.close.log on that particular day. It's s.indexmax, and I divide it by the maximum spread, which was $100, something like that, and it gives me a 10. What's that? 10. Yeah, that's not exactly what I wanted to compute. I wanted to compute the opposite, actually. You know, the percentage variation. So that's a almost 10% variation in a single day. Okay, as I mentioned, we can now go to the news and see why Google varied more than 10% or almost 10% that day. As you can see, the high was $1,097, the low was $995. It opened at 1,082 and it closed at 1,020, still with the, okay. And the volume, if we want to, for instance, imagine that I'm just trying to show you what kind of analytics we can compute. So imagine that we don't know what happened this day, but we now have an intuition that it was a particularly important day. Something happened, okay? So one thing that we want to know now is, well, maybe the negotiated volume was higher than the usual volume. So we can just see what the mean volume is. And you get that 3.4 million 3.4 million transactions of Google stock, and on that particular day you had 3.9. So it doesn't look like it was different from any particular day, and the standard deviation is more than 2 million. So yeah, volume-wise, it looks like a regular day. Unless we can do something like this, volume.plot, and we're going to get 15. And in 2018, the volume was lower than on other years, okay? So yeah, we cannot say that the mean volume was, let's say, biased lower because of the previous years or something like that. So you can see what kind of analytics we can do with this, okay? If you have any questions. Okay, so something we can do with our series and data frames is, as you could see, we could apply any. Sorry, that's not. Yes, that's good. We can apply any NumPy universal function. So that's np.maxbook, and it will apply it automatically over the columns, which is nice. That's also the same as good.max, as you can see. So by default, when you apply a reduction function, it's going to reduce over the rows. So it's going to give you one data point for each column. Okay. So if I ask, for instance, for the mean, you see that the mean higher value was $600, the mean lower value was 588, and so on and so forth. Okay. If for some reason you want to compute that function over the full value, you can of the full data frame, which is usually not what you want because different columns have different semantics. So you don't usually want to compute means over the full, let's say, two-dimensional array. But if you wanted to do that, you just do compute the mean on the means, okay, and that will work. More usually, what you want to do is to reduce over the columns, so you get somehow a different value for each day in this case, or different the mean over the rows, let's say. Okay, so as we did with NumPy arrays, instead of just doing mean without any axis parameter, you just say axis equals 1, and you just get this. Okay, and you get the mean over the column. Sometimes it does make sense, sometimes it does not. In this particular case, it does not make sense because we're averaging out higher value with lower value, with closing with open. So far, so good. But now we mix that with the volume, with the negotiated volume, which is a very high integer, which has nothing to do with the other values. For instance, if I were to plot Goog, what I would get is something like this: fixed size equals 2015. So you can see something. I get this purple line you see here is volume, as you can see over here. Okay. And the other series, which are the high, the low, the open, they are indistinguishable because, as you could see, if you find the means of the series, the negotiated volume mean is 3.5 million almost, and all the others are in the 500 range. So it's completely indistinguishable. If for some reason you want this plot to be readable, then what you can do is just log y equals true. Sorry, let's plot log y equals true, and it will use a logarithmic y-axis. Sorry, again, fixed size equals 2015. Okay, I already did that. Sorry. And as you can see, well, it's still not very distinguishable, but at least now you have different series. Okay. What you cannot distinguish at this time is high from the low, from the open, from the close, from the adjusted close, because they are very similar values when compared to volume. But at least you can see something. Okay. We will cover how to plot as a, let's say, transversal topic across the class, because you have because yeah, it's not probably something that it's very important. But by the way, besides the video, you're going to have notebooks for all the topics we're going to cover today, and even more than what we can cover today, so that you will have a, let's say, pretty handy manual for pandas. I will also give you the reference to the Wes McKinney book. Remember that Wes McKinney was the guy who wrote pandas, and the book he wrote on pandas, which is a very nice book. And in fact, all the things that I'm telling you right now and the notebooks I will give you, which are already in Aula Sesga, are based on that book. Okay. So if you are studying in A Coruña, you have kind of quite a lot of copies of that book in the library, in the computer science school. And if not, you probably have some school nearby that has a copy. Okay. So one thing you can do with now let's focus on series is to apply. I was talking about applying the mean or applying the max or whatever, or doing operations between two different series. But what you can do is to apply any ad hoc function that you happen to program. Imagine that you wanted, for instance, to given this you can do in different ways, but imagine that you want to get the power of 2 of all the values of the series. You can define a function pow2, which receives a value x and returns x to the power of 2. Okay, and now you can apply that over a series. For instance, goog.close, that will be the series, that apply pow2. And what it does is to just compute that function element-wise over the series. Okay, and you get, well, whatever you have to get. Okay, even better, you can do a function. You can apply a function over a data frame, and then it will be applied over each series in isolation. So imagine that I want, for instance, to compute the distance from each data point to the maximum in the series. Okay, you could do something like this. You define a function which receives x. Now x is a data frame, and it returns x.max minus. Sorry, I'm going to apply the series. So x, yeah, let's over that. So x.max minus x.mean. That will return is spread, let's say. Okay, so you can do goog.apply f, and you get for each. The function is now applied over the columns. So you get for each column the distance between the maximum and the minimum value. If I want to apply that over the rows, you can just use axis equals 1, and it will apply it over rows. No difference in that. If instead of the spread, instead of doing that, let me show you this. I don't know whether we mentioned lambda functions, but we can have this x.max minus x.mean. Okay, this is very useful when you don't want to name a function. You just want to use it, and there's no reason why you will want to use it later on. So you just use a lambda function. What you're doing here is exactly the same as we did before. You are defining an unnamed function which receives x and returns x.max minus x.mean. Okay. Notice that lambda functions cannot have any complex control flow like ifs or fors or whatever. It just needs to be return expression. Okay, so you can do this. Lambda x.max minus x.mean is exactly the same as we did before. Okay, and if we want to compute, for instance, the distance between each point and the maximum of the series, you can do this. Okay, x.max minus x, or x minus x.max, it doesn't matter. And then what you're doing is essentially picture how this works. X.max, it's receiving a series. Okay, this is a data frame. X.max is receiving the apply is being applied over each column independently. So the x here is a series. X.max is the maximum value of the series, and x is a series. So this is a broadcasting operation. X.max is a scalar which will be broadcasted over the full series, and then it will have the series subtracted. So as you can see, you get the distance between the maximum and each particular value of the series. Okay. Okay. Any questions? You can do some more things with data frames. For instance, you have info. It's a very useful, from the low-level point of view, function which will give you some high-level information about the data frame. So, for instance, goog.info returns that this is a date time indexed data frame. So you have 2,314 entries, and that go from the 4th of January 2010 to the 14th of March 2019, and you have 6 data columns with, and it gives you the types. If you want kind of statistics, instead of using info, you can use describe, and it will give you a very nice data frame which has as many columns as columns have the original data frame, and it has by rows the count, that's the number of values of non-null values, the mean for each series, the standard deviation, minimum, and the the quartiles and also the max. Okay, so it's a very nice, let's say, approaching function. Whenever you receive a new data frame, you want to see how it breathes. Let's say, just use describe, and it will give you some interesting statistics about your data frame. So now, let's talk a bit about how to acquire data. So as you could see, what I used right now was a data frame which I got from a very nice function, which was get data Yahoo, which was on a module called Pandas Data Reader. But at the end of the day, you want to be able to interface with real data sources. You want to interact with maybe files, maybe CSV files. If you don't know what CSV is, that stands for comma separated values. Okay, so that those are files which have kind of each row is a data row, and columns are separated by commas in the file. If you don't know about that, you may want to open Excel files. You may want to open maybe SQL databases, or you may want to open web APIs, whatever. Okay, so you can do all of that using Pandas. We are not going to go much into the syntax of that because it's really not useful to just cover that in this class. So what you have is, I'm going to show you right now. If you go to, let me share my screen a different way. Go to share my full screen for a second. So if you will, if we go to Aula Cesga, you can see here you go to the data analytics with HPC course, you have documents, you have lesson 3, you have notebooks. There you have plenty of notebooks that I added yesterday. So you have a Pandas introduction, which covers everything we have been seeing so far. Pandas Data I/O, which is what we are going to work with. Data wrangling, we won't have much time to work with that, or plotting, but I will show you the notebooks really fast, but so you can see what kind of information you have there. We are going to work a bit with aggregation. That's very nice, and that you probably want to use. And you also have a notebook on time series. Time series are just data frames and series which are indexed using dates. So exactly what we have been using up until now. They have some particularities with respect to other data frames and series, which is, for instance, they accept indexing using strings, which are automatically converted to dates. But so this notebook is a very simple one, which discusses a bit concepts on time series. But as I mentioned, we are going to work. We're going to work mainly with the intro, which is what we covered up until now, and the aggregation. And now I'm going to acquire some data from this XLS you have here, which has data from a electricity bill. And I'm going to show you kind of what you can do with Pandas, kind of as a mix of data wrangling and plotting. And then we're going to skip the data wrangling and plotting notebooks. You can delve deeper in them when you need them. Okay. So I'm going to download the Pandas Data I/O notebook right now, and I'm going to cover it a bit. But you can look at it either on the streaming feed, or you can open them yourselves in your computer. Okay. So if you see that, let's J is going to unzip the IPNB file, which has the notebook, and then a files06 folder, which contains example files. I'm not going to use example files, but the notebook depends on them. So what I'm going to do is to open a notebook here. Hopefully, that's very nice. I'm going to open notebooks, and I'm going to open pandas.io. Okay. Just to very quickly go over it so that you can see what you have in there. Okay. As you can see, you have, so summarizing, the data IO goes, the notebook goes over what you can do or different ways in which you can acquire data. So for instance, this is a CSV file, which I mentioned before. And as you can see, it's just a file containing comma-separated values. You can just read that using read CSV, and you'll get that data frame, as you can see. If you, instead of using read CSV, use a file which is called, yeah, it was read table before, but now read CSV does everything. You can specify, for instance, whether you have a particular row, which is a header. You can specify whether you have a particular format for comments which shouldn't be used. You can specify different formats of the CSV, really. Okay, so you have different ways of doing that in this section. You have a section which is really not important, but it's useful sometimes, which is how to read files in chunks. So one thing I mentioned last day was that one limitation of Pandas is that it is only capable of working with data which is already in your memory. Sorry, which fits your memory. It will load all data you in the data frame in memory. It will not do something more, or it will not do something smarter, like, for instance, an SQL database, which will be able to bring data into memory when it needs it or anything. It will just try to load everything at the same time in memory. So it's not really feasible for big data processing. So you might just want to read your files in chunks. And if you want to compute, for instance, the mean of a particular column, you can do just that manually by opening the files in chunks. That's not good enough. So we will see how to use a higher level library. It's not exactly higher level, but geared towards big data. And it's called Dask, and it's based in Pandas, but we will see that later on in a couple of weeks' time. Okay, but this is what you can do from the Pandas point of view. If your data don't fit memory, you can just read files in chunks, and that's that. Okay. Good. So just to summarize or to very quickly go over some things you can do to acquire data. If you do pd read underscore and you just hit tab a couple of times, you will get all the conditions for functions which start in Pandas with read underscore. And all those are data acquisition functions. And as you can see, you can acquire data from clipboard, from CSV, from Excel, from file formats, HDF, HTML, JSON, and message back. Lots of different things, from Pickle, from SAS files, SQL, etc. Okay. One particularly nice thing is to be able to read from clipboard, because that solves the problem that we had last day. You remember that last day we were parsing one MarketWatch web page, which was a painful one to parse because it was, of course, HTML. So it was this page, and this was the example in the 04 notebook. But you remember it was this page, the page with the stock options of Tesla. Okay. If you want to parse this table, one option was to use the code, the HTML parsing code we used last day. Otherwise, we can just select everything. Well, I'm not select everything, but just these rows. Control C, and now I go to my Qt console, and I read from the clipboard. Okay, and I will get a data frame containing the table, as you can see. It's very simple in the sense that the only thing it's going to do is to parse white space as column jumps and parse different rows. Okay, but still, it's quite nice. As you can see, we have saved all the HTML parsing we had to do last day, which was quite painful. Okay. Okay. You can write also your data. So imagine that you have a data frame, such as the Google data frame we have. So if you write .to underscore and you hit tab, you will get all the completions you have. So as you can see, you can send that to the clipboard, to CSV, to dense NumPy. I don't know what dense is. Dense representation. Yeah, that only makes sense when you have nouns, I guess. Okay. To a dictionary, so you can convert that to a dictionary object, as you can see. That's sometimes useful. You can move that to Excel, to HTML, to HDF, to LaTeX, which is very useful when you're writing, for instance, science papers. If you're writing a paper and you have your experiments, you can parse them, your results, for instance, in Python using pandas, and you build your tables, and you can compute your statistics, and you can even auto-generate your figures and your tables using pandas. I've been doing that for a few years now, and I can tell you it's amazing from the point of view of writing scientific papers. Okay. You can send that to Pickle, to SQL, to an SQL database. You can do plenty of useful stuff with the data frame object. Okay. Something you can do is read from and write to binary formats, for instance, Pickle or Excel files. I'm going to show you an Excel example later. You can interact with SQL databases. I'm not going to go deeper into this particular point, but just so that you can see that it's pretty easy. You can just create a connection using, for instance, SQLite. So you create your connection like let's connect to a database which is stored in memory. Okay, so you create your connection, you create a table, and then you can do things like this. SQL, and as you can see, SQL is a package which is pandas.io.sql. Okay, and you can do sql.readsql, select star from test, and over the connection. So you can just write SQL queries and have them execute on an SQL connection and return a data frame. Okay? And you can also use pd.readsql. That's exactly the same thing. Okay, so just pd.readsql works. In this last section on using value objects, I recommend you disregard it. It's a nice idea, but it's probably not the most useful one. Okay. So, do you have any questions with what we have been seeing so far? Sure, again, my Qt console. Okay. So if no questions, what I'm going to do is to show you an example of how to read an Excel file and do something useful with it. And then we can have a small break. Okay. So as you could see, you had in the Aula Cesga, in the notebooks folder, you had an electricidad.xls file. So I'm going to download that right now, and I'm going to open it. Okay. So I downloaded it to a folder called descargas.xls. Okay. So I'm going to just open that. So I can do df, that stands for data frame, equals pd.readExcel, and I pass the path. Descargas.electricidad.xls. Sorry about the. It's nice that the Qt console opens the IDE window to give me feedback about the functions I'm using, but sometimes it gets in the middle of things. So I can open that as a data frame. Probably let me show you my full screen just for 1 second so that I can show you what the file contains, which is probably useful for you at this point. So I share my entire screen, or even better, let me just I shared just the we need, which is this. Okay, so this is what the file contains. As you can see, this is a bill from Gas Natural Fenosa, which contains data from for the month of essentially April 2017. And you have here dates. That's what fecha stands for. You have the hour. So that's, for instance, this is 12 p.m. This is 1 p.m., 2 p.m., etc. You have tipo consumo, which is only useful for not for residential clients like this one. So this is the how many kilowatts per hour you get per hour, and this is how much it did cost, I think, in euros per kilowatt hour, I think, and this is the euros total you're spending. Okay, so as you can see, what I'm interested in is this table here. Okay, and take note of something. Actually, the table starts in row 13. So before you have some data identifying the consumer and etc. But the actual data starts on row 13. And if you go until the end of the XLS folder, you get something like, at the end, you have kind of a brief summary of everything. So how much you consumed, how much it costs on average, and how much they are charging for that. Okay, so it ends on row 757. So if I want to parse that using pandas, I'm going to close this, and I'm going to share now my Qt console again. If I want to parse that using pandas, I just use read Excel, and you will see that my data frame, the first rows contain the, let's say, identification rows that you had at the beginning of the Excel folder or the Excel file, and it's only in row 10 where I have my header actually. Okay, so what I can do is to use some parameters to change how I'm reading the file. So I can use df equals read Excel that file, but I'm going to say skip rows, and I say you skip 12 rows at the beginning of the file. Okay, and now I get this. Since I skipped the first 12 rows, and now I have the first row. Actually, it was my header row, so now it worked nicely. But if I look at the end, I still have the summary rows that were trailing the actual bill. So now I need to add another parameter, which is skip footer. Okay, skip footer, 8 rows at the end. Okay, and now you can see that I get my actual data rows, both in the header and the footer of my data frame. Okay. And now I'm going to use, so as I mentioned, I'm going to skip the notebooks which contain information about cleaning data and etc. You have plenty of information there, but what I'm going to do is to show you a practical example of what's in there. Okay, so one thing sometimes we want to do is to drop columns because they are not useful for us. Okay, in this particular example, this tipo consumo column means the kind of energy consumed is always the same. You can check that's correct by doing this. Data frame in tipo consumo column dot value counts. Okay, and it tells us that it's 744 times energía activa total. It always contains the same. It's not useful for a residential client such as this bill. Okay, so you can just drop this column, and you can do this using a function called drop, df.drop, and now you say the name of the column. Okay, and what this returns, drop by default works over the rows. So I need to add axis equals 1. So I need to tell it it's a column what I want to drop. Okay, and it will return by default a data frame without that column. Since I just want to drop this for real, what I can do is to use another parameter, which is in place equals true, which means do not return another data frame, which is the same as this, but without that column. It's just drop the column from the original data frame. Okay, that doesn't return anything. And now what you have is this. Okay. Now, for instance, everything there is in Spanish. So maybe we want to rename that. So if you want to rename columns, you can use the rename function. That will be columns equals. And now you provide here a dictionary, which contains the current name of the column, for instance, fecha, and that means date in Spanish. Okay. You have hora, and that will mean time. You have consumo, kilowatts hour, and you can just say kilowatts hour. You have a really big name, which is this. I'm going to just copy paste. And that's the euros per kilowatt hour, so that I can say, for instance, price, something like that. So it is short and to the point. And I have importe horario de energía in euros, which means how much I'm actually charged for that hour. Okay, so I copy paste and I say total, for instance. Okay, and if I run this as is, it's going to return a data frame with the new column names, as you can see. But since I don't want to keep the old names, I just can say in place equals true. And then I just make the modifications on top of the data frame I was using. Okay. So as you can see, I have a very nice data frame here. Okay. Now I can work with this. Things I can do. For instance, imagine that you want to double check that your electric provider is not ripping you off. You want to check whether the bill is correctly billed. So you can do just df.kilowatts hour, multiply that by df.price. So what you're doing is actually multiplying how many kilowatts per hour you spent in each particular hour of this bill. You multiply it by the price in that hour, and you subtract from the total. And you should get 0 for each data point, actually, more or less. Okay. And you see the results, and you see that this is 4.9 times 10 to the power of minus 13. That's actually 0. 2 to the power of times 10 to the power of minus 13, minus 19. As you can see, they all seem to be very small numbers. So what I can do is to, for instance, see what's the maximum deviation I have. So I just get this, compute the absolute value, and over that I compute the maximum. And I see that the maximum deviation on the price I'm being charged with respect to the actual price that should be charged, it's 5 times 10 to the power of minus 13. So that's actually very low and attributable to rounding errors in the float data types. Okay. And I can even do something like sum, which is if they are being honest with me, the rounding errors, the positive rounding errors should more or less be compensated by the negative rounding errors, and the sum should be more or less 0. Okay, and you see that the sum is minus 5.15 to the power of times 10 to the power of minus 12. Since that's negative, it means that they are actually charging me minus 5 times 10 to the power of minus 12 euros less than they should. So still, I mean, this is so what I can see there is that it doesn't accumulate to a number which is high, even though each entry is very small. If we start accumulating them, maybe they go higher, but this is not the case. So that's correct. Imagine now that I want to plot my data. Okay, and I can do something nice, which is, okay, I have this data frame. I want to know whether when I'm spending my my money, when I'm consuming more. Okay. So if you look at my full data frame, you can just do this df.plot, sorry, df.kilowatt hour, okay, and I'm going to plot that. Okay, peak size 2015. Okay, and this is what you get. As you can see, it gives you the instant the kilowatts per hour that you consumed by each hour, and it does this line plot. Maybe the line plot is not the best one. Maybe we can ask for a bar plot. Okay. It's computing, should be pretty fast, but yeah, 3 bars. But this is just making a point. So let's go back to the lines. I have 2 issues here. First, it's very hard to see anything here because I have lots of spikes, but what does this spike correspond to when I have more than 700 data points? This is not very interesting. And even if I look at my index, this data frame is not very well indexed. You can see that there's a correlative integers here. If I look at my data frame, I just have a dummy index 0, 1, 2, 3, 4 up until 700 and something. But I do have dates and times. I should use dates and times to index my data frame, so I can so I can somehow let's say use this to do some kind of data analytics. Okay, so maybe what I can do is to just pick date time and use that to build a date time index, such as we had on the Google series, on the Google data frame. Okay, so I can do that by just, well, I have a small problem. Is that you can check that df.date, if I just get the first of them, it's not actually a date, it's a string. Okay? So I will want to convert that to a date time object so I can build a date time index. Okay, and the way to do that is to actually use this function, pd.datetime .strptime, which converts a string to a time object. Okay, and I pass my string, which will be df.date.ilog0. I pass a format, which will be %d, which is day, / %m, which is months, / %y, which is capital Y, which is a year using 4 digits. Okay, and this is what I will get. Daytime object, which actually represents April the 4th, 2017. Okay. So if I want to apply this to the full column, I can use apply, as we saw before. We can apply pd.datetime strptime. And our only problem here is that we need to provide this string, which is the format, to the invocation. So we can use args equals, and I pass an array of arguments, and it's %d / %m / %Y. And I invoke it like this. And what I'm saying is invoke pd.datetime.strptime for each entry in my df.date column, but pass not only the value of the column, but also a second argument, which is this string. Okay, and if I do this, then I will get apparently a very similar series, but now these are date time objects. So I can just use this and say df.setIndex this, okay, and you will get a date time index. If you do that, just this and .index, you get a date time index, as you can see. So this will be now a time series, and I could index it like I indexed my Google data frame. Okay, but I can do better because I not only have the date, but I also have the time. So instead of parsing just the date, I can do df.setIn. I can call something like this: pd.datetime.strptime and df.date.ilog0 plus space, let's say, plus df.date.ilog0.hour, and say that there's a space in the format, and then I have %h. Okay, so that's the hour. Sorry, what? Oh, sorry, it's called time, not hour. Okay. Oh, it's not time. Let's see. It is time. Oh, sorry, it's df.time.ilog0. Okay. But this is an int64, so this I need to convert the string or to concatenate both strings. Okay, so so that you can see what I'm applying strp time over. I'm going to show you the result of running this. Control-C, Control-V, and that's just the string for the date and then the string for the time, which is 0. If you want to make it a bit more readable for humans, you can just now concatenate 2.00. Okay, so you'll have something like this: a date and a time. Okay, and what I did was to compute pd.date and strp time over that string and say, okay, now the format, pay attention, is the day / the month / the year using 4 digits, a space, and then %h, which is the time of day. Okay, and it converts it to a date time. So if I want to, just 1 second. Sorry, I was saying, I want to apply this strp time over the full array. So I can do df.date, I have this, I add df.time, but now I have a problem, which is that I'm trying to add together strings and integers, so I can try to do as type str. That works, but I forgot to leave a space in between both. And so we feel more comfortable because we are only humans. I can just add 2.00. Okay, and that's what you get. Over this, which is a series, I apply the function pd.datetime.strp_time, and I add an argument, which is the format, which is day / month / year, capital Y, space /h, which is the hour, colon /capital M, which is minutes. Okay? And I execute just that, and that hopefully, yeah, I'm missing double quote there, and that hopefully will return a date time series. I mean, a series of objects which are date times. And now I can use this to just df.setIndex, okay? So that now my data frame is indexed using date time objects, okay? I'm going to use inplace = true, which means, as before, just change my index on the object I'm currently using, don't return it. So now, as you can see, I have that, and I can do very nice log, for instance, 2017-04-17, and it will return all the data points for that day, and I can just add, for instance, the 1800. Yes. It will return the data point for 6 p.m. on that particular day. Okay. Nice. So now this is redundant, the date and time columns. So I can just df.drop date time on axis 1, and that drops my columns. Okay, so inplace = true, and I have now an even nicer data frame on which to operate. Okay, the good part is that I can now plot that the kwh.plot, and now my plots fixed size 2015. Whoa. But df.kwh.plot fixed size 2015. And now, as you can see, this axis, the x-axis, is now much better because it's May 2017 and April 2017, and it has days. It's still small in the sense that I have too many data points, but it's still nice. If I were to open a window, instead of, as you can see, I'm just inlining my graphs inside the Qt console screen. But I could just open a new window, which I'm not going to do because it requires me to share my full screen, and I don't want to lose time with that. But I could zoom in on any region of the plot, and then I will get the x-axis zoomed in, and I will be able to see more clearly the data. For instance, imagine that I want to see a particular day. I can just df.log 2017 04017, for instance. I think this was in the index, okay? And I can just plot this using kind equals bar, and I can see, sorry, it's fixed size equals 2015. Hopefully now I can see a better plot. So this is all my series. I just want the kilowatts per hour, for instance. So this is what I consumed for each particular time of the day. So as you can see, the top consumption was at 8 p.m. and that's that, okay? That's for a particular day. Okay, any questions up until now? Just we have 5 short minutes before we break. So if no questions, let's just do the last interesting thing, which is, imagine that I want to know when, so this is just, this picture I'm showing you, this graph is just a particular day, April 17th, but it might not be representative of what I do on a daily basis. So maybe what I want to do is to find the average for each particular day, okay? And this is a new operation that we haven't seen yet, that is a group by. I want to group all my data. So here I have a data frame which contains data for different days, but the different days have, of course, as you know, each day has 24 hours and the hours repeat over and over again. So for the 4th of April, I have 12 a.m. For the 5th of April, I have 12 a.m. For the 6th of April, I have 12 a.m. And I have 12 a.m. for the 4th of May, for the 5th of May, and for every single day, okay? So I might want to compute the mean for instance, 12 a.m. And I can do that easily by just saying df.index.hour. This is a particularity of my daytime index. Sorry. Why not? If that index, this is a daytime index, is it not? Index. Okay. That hour. Oh, sorry, maybe it's hour with the small h. Okay, yeah. So if I say df.index, that's all my index points. If I say .hour, that's a very nice accessor, which is extracting the particular hour point for each index. Okay, so it will return this integers from 0 to 23. If I want to compare that to 0, I have a bool which contains true whenever the index is 0. And since this is a bool, I can use it to index my data frame. You get all the data points which are acquired at 12 a.m. And I can now compute the mean, for instance. And I see that I consume on average 0.3 kilowatts per hour, and the average price for that is 0.07 euros per kilowatt hour, and that yields 0.02 cents for the average day on this bill. If I did sum, I will get the sums of the kilowatt hour. The price is the sum of the prices, which does not make much sense, and the total money I spent for the energy I consumed on 12 a.m. Okay, but if I want to do this for all the hours, that will be a bit not nice. I mean, I will have to repeat this, okay, for all the possible values of df.hour, one for 12 a.m., 1 a.m., and 2 a.m. up until 23, which will be 11 p.m. Okay, but there's a better way to do this. It's just to say df.index.hour. These are 744 values. I can do df.groupby that. Okay. And that's a very nice function, which is going to return what calls a data frame group by. So imagine that what this object is 24 different data frames, which are sub-data frames of the original one, in which each sub-data frame contains the points which share the same hour value. Okay. And now I can do this. The mean over the group by object. And it will return exactly what we wanted. It's the mean or the average kilowatts hour consumed for each different hour of the day. So now I can just extract kilowatts hour and plot using kind equals bar, and fixed size equals 2015. And I get this, which is now, as you can see, it's substantially different from the day I just picked at random, which is the average consumption in this energy field for each different time. Okay. So this is essentially, let's say, pandas in a nutshell. Okay. Now we're going to go for a small break, and we are going to devote the remainder of the class to just show you different examples, and I will give you some time to go over the examples yourselves, because I think it's also nice to have some, let's say, me time with the library to get the feel of it. But before we break, do you have? Sorry, I'm just now in your question. What was that last command at like 5 minutes ago? What command were you asking about? Okay, so it's all good. Okay, so any questions now before we make the break? Okay, so let's go for a 20 minutes break. So that's at 6:30 p.m. We come back. Okay. I'm not going to stop the recording because that will probably mean that in YouTube we will have two different recordings for this class. So it's better to just have one with 20 minutes, let's say, silence, than to have two different links for one class. So I'm just going to mute my microphone and return in 20 minutes. See you then. Okay, let's resume the class. Welcome back. Are you back yet? Okay, let's. Oops, sorry. Resume the class. I had to mute the YouTube stream. So I'm going to show you quickly what I'm leaving for you in the related to how to do data wrangling and plotting with pandas, which we are not going to cover in detail now. Let me change what I'm sharing. I don't know why. Keep coming back to this. Okay. So I'm going to share my entire screen. You have here in Aula Cesga, you have two different notebooks. One's called data wrangling, and the other pandas plotting. So if you download those two, now I'm going to so maybe it's wrong. Yep. Now I created those files wrong. So keep in mind that the extension is wrong. It shouldn't be BZ2. It should be GZ. So I will correct it later. But if you want to open them now, keep that in mind. Okay, they are gzip files and not bzip2 files. Okay, maybe I can just rename them here. Not. That's probably only the title and not the name it will give to the file once it's downloaded. No, it's still being kept. Yeah, I will change them later. But remember, they are GZ files. Okay, at this time. Tomorrow they will be set to correctly. So if I go to my notebooks here, I've downloaded these two files, and you have this data wrangling notebook. It takes sometimes a while to load. And you have here, so data wrangling, as you may know, is the name we use to denote the operations that have to do with cleaning data, changing the shape of the data, and making the data more amenable to what we want to do. So here, this notebook is going to cover operations such as merge between different data frames. It's going to cover also, this join operation, which is just merges over the indices of the data frames, but it's just syntactic sugar for merge on the indices. Concatenating data frames. You can concatenate data frames on the rows or on the columns. So you can, for instance, create a data frame by concatenating together different series. You have plenty of examples over there. You have how to reshape and pivot data. So for instance, imagine that you have this, you have this data frame. And imagine that somehow I'm going to change this. So we have .index.date, .index.time. So that's, if you look at the index, which is here, it's timestamps. So they have a date and they have a time. So I'm going to separate them. So it's the opposite step of what I did before. So let's say df in date is equal to df.index.date. And df in time is equals to df.index.time. Okay. So now you have equal date and time exactly as I had before. So instead of working with just one object, which is what I have here, a datetime object which fuses together the date and the time, I can work with what's called a hierarchical index. So I can set the index to be date and time. And in place equals true. And now you will see what this is doing. You can see now I do have two different indices, date and time. These are what they are called, what is called hierarchical indices. So I have two different columns working as an index together. It's kind of when in SQL you use a key which is composed of different columns. Okay, so I can now, for instance, do something like this: df.unstack. And what that's going to do is it's going to change my inner index, which is the column index. It's going to move it to the columns. Okay, and you get something like this. You get an index which is date, and you get hierarchical columns, which, as you can see, have the kilowatts per hour, the price, and the total. And for each first order column, you have all the possible values of the time, which is 12 p.m., 12 a.m., 1 a.m., 2 p.m., 2 a.m., etc., etc. Okay, so it's kind of how to change the dimensionality of the data. Okay, so you have your data frame, you can unstack. Okay, that's moving indices in the rows to the columns, and you can also stack, which is the opposite operation. Okay, so if I unstack and then stack, I get exactly the same as I had in the beginning. Okay, so that's something you also can do, changing how your data frame looks. You can transpose your data frame. So if I transpose my data frame, what I'm actually doing is changing the columns by the rows. So now, instead of having a data frame with 744 data points for 3 different series, I have a data frame which has 3 different data points for 744 different series. One series for each date time, and the index is kilowatts hour, price, and total. Okay, doesn't make much sense with this particular data frame, but might do with others. You have different. That's really interesting at this point. You can remove duplicates, of course. You can even ask what indices are duplicated automatically. Okay, and you can rename, but we have already seen this very quickly with the electric bill example. But that's the idea. Okay, you have something which is interesting, which is discretization and binning, which is how to compute, for instance, quantiles, quartiles, and how to bin together, or how to get categories for our continuous data. But we'll see that later with an example. Okay? You can detect and filter outliers, etc., etc. Okay, so you have plenty of small examples in this notebook, and then at the end you have a larger example, which shows you how to work with a database which contains data from an USDA food database. This is the US Department of Agriculture. So they have a database of food nutrient, which contains things like this: Kentucky Fried Chicken, extra crispy wings. That's made by KFC, Kentucky Fried Chicken. It's fast food, which contains, for instance, 68 grams per portion. It has nutrients such as, for instance, 20.8 grams of proteins. Okay, that's of course many more data in this entry, but that's what you have. You have thousands of foods, and you have the nutritional data for them. So what we do in this example is to read a JSON file using pandas. We convert that to data frames, and we merge them and do things with them. Okay, this is a very large example. I'm not going to cover it because it will take quite a lot of time. So this I suggest you try to go over this final example of the Pandas data wrangling notebook to work a bit with Pandas this week. You don't need to go over the previous sections of the notebook, which present very small examples. What I suggest you do is, for instance, you are doing this large example with the USDA food database. If you find, for instance, that you don't understand exactly how this rename function works, then you have rename examples to go over in the beginning of the notebook. Okay, so I would approach it that way. Go for the big example, and if I have any questions about how anything works, first try to locate the small examples and the explanations in the notebook. And if that's not clear enough, then just shoot me an email and we'll go over it. Okay. So that's for the data wrangling notebook. Any questions regarding this? Okay, so I'm moving to the plotting notebook, and that's, we have already seen a few examples of how to plot, but I want to point you to a particular interesting example here. So you have here, we have already seen how to plot with the electric bill example. You have bar charts, you have line charts, you have lots of things. But one thing that might be interesting for you at some point is how to plot map data. So what this example shows here is a larger or large-ish example showing a case study, is a parse and data analysis of data from the what's the name? The earthquake in Haiti in 2010, extracted from a database which is from a company which is called Ushahidi, which is a non-profit company which kind of takes alerts using SMS messages. Okay, and all that data regarding the 2010 Haiti earthquake is in this CSV file. So as you can see, that's almost 3,600 entries containing data such as where the incident happened in latitude and longitude, the title, the date, and the description. Okay, so things that you might have there. I don't have any particular one, but you have here, for instance, emergencies of public health and etc. Okay, so what this example does is to filter the data, because it has outliers that shouldn't be there, because if you look at the GPS coordinates, they are not in Haiti. So it filters the data and it parses the data to show maps of different types of emergencies, for instance, food shortages, emergencies, regular emergencies, medical equipment and supply needs, and food distribution points on the map of Haiti. Okay, and it plots each incident on this map, as you can see there. And then noting that most incidents occur in that section over there, that actually is Port-au-Prince, which is the capital of Haiti. So it zooms in and shows you how to plot roads and other shape files, which are vector files on top of maps. Okay, so that's also, if at some point there's no point in covering this in this class, because that's a very particular use case, which is plotting maps. And the more simple ones we already covered with the electric bill example. But just I wanted you to point to that particular example in case you need it for any reason. Okay. Again, if you have any questions, just shoot me an email and we'll try to solve them. Okay. And the thing I want to cover in more detail until the end of this class is how to work with the group by operation that we just saw before at the end of the electric bill example. So I'm going to share again my Qt console screen. Okay, stop sharing this and share my application window. Okay, and we're going to work with that. Okay, so let me, with these notebooks I downloaded, 7 and 8, there's a particular file I want to point you to, which is, 508. There's, oh, it's not 508. Yeah, I didn't download it yet. So it's in notebook 09, I think, which I didn't download yet. It's, yeah, the notebook 09 pandas aggregation that I want to look at now. So I need to, I'm just uncompressing it on my file system. And it has a files 09. It has a CSV file which is called tips. If you take a look at it, you will see that that's a comma-separated value which contains columns called total bill, tip, sex, smoker, day, time, and size. Okay, and I'm going to read that in pandas using pd.readCSV. Oops. And you can see that now in a data frame format. So that's actually a very famous data set, which ships with R, if I'm not wrong, and I think with ggplot or something, package from R. And it contains data from a restaurant containing data on bills and how much people tipped, and whether the person paying for the bill was male or female, whether they were sitting in a smoker or non-smoker section of the restaurant, and which day of the week this happened, and whether it was for dinner or for lunch, and the size of the party. So that's how many people were having lunch together. Okay, so you can already see, well, this has 244 data points, so it's not the largest data set out there, but it will be useful for exemplifying some things you can do with pandas. Okay, so one thing we can do here is imagine, so we have, for instance, this is data from the US. So as you know, it's customary to tip a given percentage. So we can compute how much for this for each total bill, how which percentage of the bill the tip represents. So that will be df.tip. We divided it by df.total bill, and what we're going to get is a new series, which will contain the percentage of the tip on the bill. Okay, we want to keep that. So the way to create a new column will be this. We just we use the bracket accessor to access a column which does not yet exist. And pandas is smart enough to know that then what we want to do is to add a new column there. Okay? So what we do is just to put that tip percentage there. And let's see, for instance, whether the party size, the number of people having dinner, makes a difference in the tip percentage. Okay, so let's compute, for instance, the means for these values. And you can see that the mean tip is usually 16%. And we can ask ourselves whether the size matters, and we just group by size. And remember that what I did in the previous example was to group by, if you remember, oh, sorry. Should not do what I want to do here. You have to group by df.index.hour, okay? And you remember that df.index.hour was an array of values, the same shape as df. And what group by did was to group by them. So when I want to do that, I can group by df.size, and that will be exactly the same. I'm passing an array of size, the same size as df. Or I can just say, if it's a column I want to use, I can use the name of the column. df.group by size, that works and groups by size. I now compute the means. Okay, and you can see that for parties of size 1, the total bill is usually 7.24, tip percentage 21%. For 2 people, that's $16, 16.5%. For 3 people, 15.2%. For 4 people, 14.6% almost. For 5 people, 14.1, and for 6 people, 15.6. So one thing we're noticing is that apparently, at least with respect to parties of size 1, the tip percentage is smaller, the more people that are sitting at a table. Okay, or so it seems. We could do something like this. For instance, imagine that I do that, and I can plot kind equals bar chart. This should work, but I'm not completely sure. Box plot is what I want to do. Box plot. It's not plot. It's a plot. It's called box. Sorry. So box, and I get this. As you can see, by default, it gives me one plot for each party size. So I have the total bills, tip size, and tip percentage for each party size there. So maybe what I can do is to group by size. Then I use tip percentage. Okay, and I have that mean. And now I just plot kind equals box. That will not work, of course. I need to do, yeah, the tip percentage dot plot kind equal a box. That should work. Okay. And now that is not very nice because it's overlapping everything on the same block. So what I need to do is to use something like subplot equals true. That might not work, but I will hopefully find out what I want. Yes, layout none. Okay, subplot. So yeah, that let me just do something just in case. Accessing the actual. So subplotting was not equal to, that was layout equals, this is 6.1, I think. It's not very nice, but might be. Yeah, that is not exactly working. I will have to check the documentation to see exactly how you want to do this, to use different subfigures, exactly the same we had in the previous example where I just did this. This was working quite well, so I don't know why it's working nicely. So I don't know why it's using just one figure to plot them together when I just extract one t percentage. Okay, but in any case, plot subplots. Oh, it's subplots, not subplot. Maybe this will work. Yeah, that's. Yeah, it seems like this version of Pandas has kind of something which is not working correctly. But the idea should be that it should open each one of them in different subplots. If not, then I can do something which is not exactly the best option, but which will be to just store this object. And then you can do O dot. That will be groups, I think. Oops. So you have a dictionary, and each element contains different plots. So if I just go over the values, I have different subplots. So I could do something like for each one of these, for subdf in each of these, I do subdf dot plot annual box. This will be actually t percentage annual box. This is not going to work, but I think the problem is we don't want to pay much attention to this. I think the only problem we're having here is that we're using inline, matplotlib inline. If I let it open different windows, this will probably work nicely. So let's just not lose any more time with this. Just you can see how the group by works, which is what I wanted to show you. Okay. So more examples. Imagine that I want to, for instance, see how the tip, a scatter plot of how the tip and the total bill are related. So I can do something like this. df.plot kind equals scatter. The x-axis, I want to see the total bill, and in the y-axis, I want to see the tip. And fixed side so that it shows nicely on the stream 2015. Okay, that's what you have there. So here we will be seeing a scatter plot of a total bill against tip, and as you can see, it kind of looks like a linear relationship, more or less. We don't have many data points, but it does look like a linear relationship between both. Okay, more or less. We will see the next day. We will see tools to actually compute linear regressions and even plot them, and it will be probably nice. Okay. Imagine that we now want to group by whether tips are large or small, and that will be tips are usually in the 15 to 20% range in the US. So let's say that a tip which is larger than 20% is large. Okay, so that will be the tip percentage larger than 0.2 will be large tips. Okay, so that gives me a Boolean array which I can use as before to index on the tip percentage larger than 0.2. I get the, let's say, large tips, and if I say less or equal than 0.2, then that's these smaller tips. Okay, but one thing I can do is group by this array, and it will create two different data sets: one which has the small tips and one which has the large ones. So I can group by that tip percentage, and I can again find the means, see whether that tells me something. Okay. And what I can see is that at first glance, I wouldn't say that there's a difference in party size. Maybe for true it's smaller, but smaller-ish, not very clear. But where there does seem to be a huge difference is in the total bill. So for large tips, the bill is usually smaller, or the mean bill at least is. So we might be onto something here, which is that there's another etiquette rule for tipping in the US, which is that you should tip 15% or more or less, 20% if you're very happy, but you should never tip less than $1. So if your total bill is less than, let's say, $7, $8, maybe you will be tipping more than 20% just because it's customary not to tip below $1. So maybe let's just do this: the F in the F, the total bill less than 10. And we can see that the tip is $2, 1.45, 1.32. That's exactly someone who wanted to add everything add to $10, $10, sorry, 1.56. That's $1, $1, $1, 1.48. So as you can see, there's no tip ever below $1. So that is connected from YouTube. Let me double check that. Yeah, the live stream I think is working again. So it might have been some problem with the connection, but I hope it's again working. So I can see that you didn't miss anything because you complained less than 1 minute ago. So I don't think anything was missing. So let's just reshare my screen and keep working on what we were checking. So what I was mentioning was that you can group by anything so long as you have an array with categories of the same size of the data. So let's do just that, which is generate something like this: tip. Let's total bill, and let's create categories for this column. Let's say that I want to divide this into 5 different categories, for instance. One easy way to do that is to use pd.cut. Say I want to cut total bill into 5 different categories. Okay. And let's say I call this cuts. Okay. And what this will return, as you can see, is a
series of the same shape of the data frame, okay? And each value has what's called a categorical value, okay? So that's, for instance, the first one, which had was $16.99, is in the category 12.62 to 22.16. So it created these I asked for 5 categories, and it created these 5 categories you have in this line, from 3 to 12, 12 to 22, 22 to 31, 31 to 41, 41 to 50. The way in which it by default creates the categories is by making all categories have the same number of data points. Okay, so the ranges might be different sizes, but each category will contain the same number of data points. And what it returns is kind of what's called a categorical data, and for each data point is one category. Okay. So this is exactly the kind of thing we can group by. We have one series which is the same number of data, the same length than our original data frame, and it has one different category for our data frame, for each entry in our data frame. So I can just use df.group by cats and compute the means. Okay, there. You can see again that for total bills in between $3 and $12, the average bill is 10, and the average party size is 2, let's say, and average tip is 19%. Between 12 and 22, the average size is a bit larger, 2.36 people, and the average tip is a bit smaller, 16.3. And when total bill is 22 to 31, then the size of the party increases and the percentage of the tip decreases, and that's always a trend. You can see as the size of the party increases, the total bill also increases, usually, of course, because there's more people eating, and the tip percentage decreases. So there's a, let's say, clear trend there. Okay. You can see that this is very nice, let's say, to be able to use cat. You also have qcat. And qcat, you can say you want to qcat was the total and integer array of quantiles. So, for instance, if I say here 10, I'm not asking for, I'm asking actually for the deciles of the distribution. Okay, so if I ask for 4, this will be cutting by the quartiles, and so on and so forth. Okay, so it works. I think it's different. It's slightly different. Okay. Polygons. Oh, yeah. No, I was wrong before. Sorry. Cat is making the ranges exactly the same size. So it cuts your total range, which goes from 12.618 to 50. No, that's not the total range. You have total bill. Just 1 second. You have to describe. The minimum goes in total bill from $3 to $50. So I don't know why pd.cut. Oh, it goes from 3 to 12. Okay. So if I do value counts. Yeah, I probably messed up in some. I'm reading that. Yeah. Okay. So yeah. Sorry, I didn't sort correctly. Maybe I can sort index. That's nicer. So you have equal size ranges. So that's more or less $9.5. So from 3 to 12.6, from 12.5 to 22, from 22 to 31.5, from 31.5 to 41, so on and so forth. But the number of data points in each category may vary. So if you use qcat, then what you have is it uses the 5 quantiles, let's say. So they are computed so that the number of data points in each quantile are exactly the same. So that's the difference between cat and qcat. You can do whatever fits better your use case, let's say. You can, for instance, group by 2 different variables. So you can do, for instance, group by smoker and say whether that has any influence on tip. It apparently not. Or you can, for instance, group by sex, okay? And that might or might not, I mean, 1% difference is not higher, it's not too high, but you can group by 2 factors. So you can group by sex and smoker, and that computes the cross values of sex and smoker, which will be female non-smoker, female smoker, and male non-smoker, and male smoker, and it gives you a hierarchical index, like you can see here, and you have one aggregate statistic or one aggregate value for each of the cross categories that you have there. Okay, so you can see, for instance, that apparently the best tippers out there are female smokers. Okay, apparently, of course, you will need to analyze data further, but this very simple statistic seems to point to that. Okay. Okay. This is almost, let's say, syntactic sugar, but it's interesting, which is pivot table. Okay. And this is a very fast way to compute group bys, specifying what you want to see in the rows, what you want to see in the columns, and how you want to aggregate things. So for instance, imagine that you want to see a group by sex and smokers, such as we did right now. Okay. This is what it will do. By default, the index tells it what do you want to group by in the rows and computes the averages. Okay, so same as before. This is not the averages. Oh yeah, it is, but it's ordered differently. Okay. Imagine that now you want to see on the values, you want not to see everything, but you want to just see the tip percentage and the party size. Okay. So you'll do something like this. You say, I want to see these 2 values in the table, and I want to group by sex and smoker. And this is exactly what it will do. It will remove the other columns there. Okay. And if you want to group by another variable, but you want that variable to be in the columns, for instance, a day, you can specify it like that. Okay. And you will have something like this. You have group by female, sex, smoker, and day. But the table is presented so that you see sex and smoker on the rows and the day on the column. So you have non-smoker females are 2.5 people on Fridays, 2.3 on Saturdays, and 3.7 on Sundays, and 2.5 again on Thursdays. Okay, and they tip 16.5 on Fridays, 14.8 on Saturdays, and 16.5 on Sundays, and 15.5 on Thursdays. You see how this works, okay? I'm saying that this is syntactic sugar because this is exactly the same as doing a group by. This will be sex, smoker, day, okay? Computing the means, but we don't want all of them. So we just select size and tip, I think it was. This is fancy indexing, okay? And now we unstack. We get the inner hierarchical index, which is day, and we stack it to the columns. Okay, as you can see, that's I think it's exactly the same as we got before. But it's still nice to have that function there. We can even change it so that if we don't want the mean to be computed by the max, for instance, we can just use AGG, which is the aggregate function. Sorry, we put that in. AGG func. Sorry. And change what you use. Okay. Okay. So I'm going to leave the class here. I'm going to show you before we leave the notebook or this particular notebook. So I'm going to again share my full screen. Okay. And I'm going to show you here the notebook on pandas aggregation. And it looks exactly like the previous notebook. So what you will have here when it loads, you will see that you have lots of small examples of how to group by with different keys, different ways to do things, okay? But at the end of the notebook, you have a larger example, a very interesting example, which looks at the Federal Election Commission database in 2012 in the presidential elections of the US in 2012. So the US election regulations require that anyone who donates money to a candidate be registered in a database. So you have that file over there. It's kind of a large-ish file. It's 122 megabytes in memory. So as you can see, that's a file which contains an ID which is unique, a candidate ID, candidate name, contributor city, state, zip code, employer, occupation, how much it is donating, and etc. So you can see things like, for instance, if you just look at one data point here. Whoop. Bye lights. Yeah, sorry, just 1 second. Our lights are dying. Yeah, that's fine now. So if you just look at one data point like this one here, you can see how, for instance, Nancy Hutker donated $25 to Barack Obama, and Nancy Hutker is a homemaker for the Hutker family in Arizona. Okay, so you have up to 1 million entries in that database containing this kind of data. Okay, so what this is a very nice example because it combines everything together. It does some cleaning of the data because, for instance, it removes all candidates which are not Barack Obama and Mitt Romney, which were the runner-ups. The ones running for the election in the end. Okay, and it does clean the data further by it just gives some examples. But for instance, you have here some people write CEO with dots in between, some people write CO without dots, and it just tries to normalize data a bit. And after it's done, so it just does analysis like this: whether how much money has been donated by attorneys, for instance, to Democrats and to Republicans, or by CEOs, or by consultants, executives, by different professions, let's say. Okay, and it does plot that, and you can see, for instance, here that people who are retired donate more money to the Democrats on average, and professors almost only donate to Democrats. People who are presidents apparently donate to Republicans. Homemakers usually donate to Republicans. You can do that kind of analysis. Okay. And get, for instance, what this example does here is get the 5 kinds of people or people by occupation who donate the more money to each candidature. So, for instance, the retired people are the top donators for both Barack Obama and Mitt Romney. And then for Obama, you have attorneys, people who that do not disclose what they do for a living, homemakers, physicians, lawyers, and consultants. And that's and for Mitt Romney, you have homemakers, attorneys, presidents, CEOs, and executives, for instance. Okay, so that's the kind of or for who do they work for? Students, volunteers, Microsoft usually donate to Barack Obama. Students, Credit Suisse, Morgan Stanley, Goldman Sachs, Barclays Capital usually donated to Mitt Romney. Okay, so that's the kind of analysis that it's being done in an example. I think it's a quite nice example. So it's possibly something you want to look at, okay? And then analysis by states, donations, and etc. Okay. So that's the notebooks that you have regarding this. You have one for introduction, one for data I/O, data wrangling, plotting, and aggregation, and then you have one on time series, which I didn't cover, which I'm just not going to show you, but it's just on time series, what you can do with time series. And the first thing you can do with time series is group by hour, etc. You already saw how that worked with the electrical bill example, and you can resample time series. So for instance, if you have a time series which has 1 data point per minute, you can resample that to have 1 data point per hour, and it will automatically, it's kind of a group by, and it will just compute aggregation statistic, for instance, means, and give you a different data frame, which has 1 entry per hour instead of 1 entry per minute. That will be super sampling, I guess. No, that will be subsampling. Or let's say decreasing the frequency. If you want to increase the frequency, then you can just interpolate values between actual data points. You can interpolate new values. Okay. So that will be what the Pandas time series data frame covers. So I'm going to stop sharing my screen now. This is what I wanted to cover today. We'll be seeing in the pandas front, let's say. So do you have any questions before we finish the class for today? Okay, so I'm going to, right after I finish here, I'm going to put on Slack the link for this stream. But other than that, try to go over these examples during the week if you have some time, and I will see you next week. Okay, thank you for being here today, and see you next week.